A very warm welcome to the lecture series of marketing research and analysis, second part. In the last lecture we were discussing about confidence interval calculation and its importance. So, we understood why confidence interval is to be understood by any researcher, what is its importance. So, there we saw if you can calculate the confidence interval, then you can know ki whether your the population mean or the sample mean, whether it lies within an acceptance region or not. If it does not lie within the region, then we say it goes out and it is a part of the rejection. So, there it helps you to test the hypothesis, whether it is the null hypothesis to be rejected or not to be rejected in one way. Continuing the same, we are today getting into hypothesis testing. So, hypothesis testing is very important for all researchers, because whoever does a research in any field of study, be it engineering, management, social sciences or medical, anywhere, everybody is interested to test a hypothesis, which is an assumption basically that they want to prove, right. So, let us see what is how do you go about testing of hypothesis. So, before we get into the first case, let me tell you what are the things we need to keep in mind while testing a hypothesis. So, the first is, when you test the hypothesis, the first thing is to develop your hypothesis. So, develop the null and the alternate, okay. This is the first step. So, once you have done with it, then the next step is you need to see the direction of the test. So, what is the direction of the test, right. Now, direction of the test we have already learnt that it can be one tailed or two tailed. So, it can move into any direction or only in one direction, maybe it is a right tailed test or it is a left tailed test, okay. Once you are done with it, then you decide, then the researcher has to decide what is the level of significance at which he wants to check, he or she wants to check, right, significance level. So, this is nothing but the alpha or the 1 minus confidence, okay. So, once that is done, then the researcher decides the test that it wants to use, which test needs to be applied in this case, in this particular case, test that needed, right, test needed, which test is needed, right. So, is it a Z test, is it a T test, then or is a case of one tailed, one sample, two sample, right, what it is, what exactly is this, or it is a case of a ANOVA or whatever, chi-square, we will see in the further classes. Finally, you calculate the test statistic. So, once you decide the test needed, then you calculate the test statistic, right. So, once you decide the test statistic, then finally you compare the test statistic with the critical value, right. So, compare the test statistic test versus the critical, right, and accordingly then you reject or accept the hypothesis, right. So, let us go to the first case. The first case today we are going to discuss is hypothesis testing of means when the population standard deviation is known. But let me tell you, this is a very rare case. The population standard deviation is generally unknown, right. You are not aware of the population. So, that is why the population parameters are mostly unknown to you. But anyway, let us assume this is the first case and you are aware of the population standard deviation. So, this case is saying that a manufacturer, you can take any manufacturer who supplies rear axles for US Postal Service mail trucks. These axles must be able to withstand 80,000 pounds. Now, what it is saying, the buyer thinks wants that the axle should be able to withstand 80,000 pounds per square inch in stress tests, but if it is excessively strong, it raises the production cost, okay. Long experience indicates that the deviation of the strength of the axles is 4,000 pounds per square inch. So, what is the deviation? 4,000 pounds per square inch, the strength needed is 80,000. The manufacturer selects a sample of 100 axles from production, tests them and finds that the mean stress of the sample, capacitor sample is 79,600. So, this is the sample value, right, sample mean per square inch. if the axle manufacturer uses a level of significance level of 5% in testing, will the axle meet his stress requirements? So, now the case is very clear to you, right. So, in a real life situation, let us assume this is a real life situation and you are facing this case. How will you attempt? So, first thing as I said is you have to develop the null and the alternate hypothesis. So, what you do is when you are going through this exercise, kindly start writing your null and the alternate, right. Once you are written, then kindly check whether we are doing the same thing or not. Okay. So, solution. So, what is saying? The mu is equal to 80,000, right. So, the null hypothesis, let us go back. The null hypothesis, let us say, must be able to withstand 80,000 pounds per square inch. So, we say, so let us assume that the mean is equal to 80,000. Okay. So, what is the alternative? That the mu is not equal to alternative. That is what the manufacturer also is concerned. If it becomes too strong, then it raises the production cost. If it is too weak, maybe it will not be acceptable to the buyers. So, mu is equal to 80,000, mu is not equal to 80,000. So, it is a clear case of a two tailed test. So, that the test can move to either direction, this side, right, the value can fall either way. The population standard deviation is known in this case. How much? Now 4,000, it was told to us. So, because the sample is a large sample, so we treat it as an infinite population. So, the normal, we use the normal distribution, correct. Had it not been infinite, we would have gone for a finite population check. So, now let us calculate the standard error. So, standard error, as you know, is nothing but standard deviation upon the root over of the sample size, right. So, in this case it is equal to standard deviation was 4,000 divided by root over of n. Now, how much was the n? 100, correct. So, that is equal to 400, right. Now, we checked at a 5% level of significance, correct. So, if you go back also 5%. So, 5% was spread up into two parts. So, that means the 95% was spread up, actually the acceptance region is 95, which is also spread up into two parts. So, how much is 0.95 divided by 2? So, that is equal to 0.475, this is one, right. So, from the normal distribution, let us find the z value for 0.475. So, if you look at the area under the curve for 0.475, so the value is 1.96, right. So, now 1.96, so let us calculate the first the confidence interval, right. So, how much is the confidence interval? So, mu is the mean, right, plus z is the 1.96, right, into the standard error. So, this formula you can write it like this, something mu plus or minus z sigma x, okay. So, that is giving us the upper limit and lower limit. So, plus and minus. So, when this value comes to us, we can now see that your value of mu was 80,000. Now, 80,000 surely lies between somewhere here, right, in between these two, right. So, the limits of the acceptance region are 80,784 and 79,216, and the sample mean is 79,600. The population was 80,000, we know that. So, since it now the hypothesized mean, let us say the sample mean lies within the acceptance region, that means this was 79,216 one side, and the other side higher upper was 80,784, and your mean somewhere let us say is 80,000 here, okay, the hypothesized mean, and your calculated the sample mean is 79,600. So, 79,600. So, the point is the 79,600 in between the acceptable limits? Now, yes, it is within the acceptable limits, that is the 79,216 and 80,784. On this basis, the manufacturer should accept the production run, because it cannot reject the null hypothesis. So, it rejects the it rather accepts the null hypothesis in simple terms you can say, and understand that the mu is equal to 80,000, that means, correct. The same thing you can do on terms of a standardized scale. Now, what is the standardized scale? So, if you remember, z is equal to, we said, x minus mu, x bar minus mu upon sigma x. So, if this z value is nothing but the standard error, right, in the standardized standard errors from the mean, right. So, let us calculate that. if you want to calculate, let us see this. So, how much is it? 79,600 minus was 80,000, okay, and divided by sigma x was, if I am not wrong, 400. Yes, sigma x was 400. So, 400. So, that is equal to minus 1, right. Your z value should lie between, for a 95% confidence level we said minus 1.96 to plus 1.96. Okay. So, if you look at it, your value is somewhere at minus 1. Now, minus 1 will be let us say somewhere here. So, it is within the acceptable limit. So, again you do not reject the null hypothesis. Okay. Now, let us take a second case. So, the second case is a case where it is a one tail test of means. Now, let us read this case. A hospital uses large quantities of a particular drug, okay, some medicine, understand. The individual dose of this medicine or drug is 100 cubic centimeters. The action of the drug is such that if you take excessive, it will harmlessly go out from the body. Suppose you take excessive of the drug, it has no implications, it has no effect, right. But if you take insufficient dose, then it does not produce the desired medical effect, rather it interferes with the patient's treatment. The hospital has purchased this drug from the same manufacturer for a number of years and knows that the population deviation, standard deviation is 2 cc, that means 2 cubic centimeter. They take they take 50 doses of this drug at random and find that the mean of these dosages are 99.75 cc. So, which suggests that it is now coming less, okay, than 100. The hospital sets a 10% level of significance. Now, if you go back and remember, now 10% level of significance, that means the manufacturer is ready to part with 10% of reject 10% of good null hypothesis, right, appropriate null hypothesis, correct null hypothesis, and asks us whether the dosage in this shipment are too small, because it is coming small. So, he is worried, is it small, because if it is small, then it will interfere with the patient's condition. How can we find the answer? So, again I would suggest, please the first thing is write your null and the alternate. Okay. So, what is the null and the alternate in this case? So, is first of all, is this a one tailed or two tailed test? Obviously, the company is not worried if the dosage is more than 100, correct. So, we are not interested in anything more than 100. So, we are only interested in the less than 100 case, right. So, obviously, it is a one tail test, correct. So, which tail, which side? Obviously, the left side, the lower side, okay. So, let us see. So, in this case your mu is equal to hypothesized mean is equal to 100, standard deviation is 2, n is equal to 50 sample size, the sample mean is 99.75, yes, right. So, now what is the hypothesis? Now, mu is equal to 100. What is of interest to us is mu is less than 100. If it is less than 100, whether it is less than 100 or not, that is what the researcher is interested, he is not interested for the other side. So, first you may do one thing, you can just simply write the first one, the one that is you are interested, and automatically when you are interested in, you are writing this, then you go for this. This can be also a very nice way of writing hypothesis, okay, or framing the hypothesis. Alpha is given to you, right. So, for a 10% level of significance for at a one tail test, you need to find out the z value, right. Okay. So, what is saying? Population standard deviation is known to us and n is larger than 30, correct. N is larger than 30, you have taken 50, right. We can use the normal distribution. So, the value of z for 40% of the area under the curve is 1.28. Now, let us look at it. Why this is saying 40%? What is the reason it says 40%? Okay, let us understand this first. Let us draw it. We are not interested for this zone at all, correct, the right side. We are interested only for the left side. So, the left side, so the significance level was 10%. So, rejection was 10%, right. So, what is left? So, this entire zone was 0.5, right, this was 0.5, this was 0.5, correct. So, 10% has gone into the rejection. So, what is left? 0.4, correct. So, this 40% area under the curve, this area under the curve is equal to 1.28, it says. So, because it is left tail, so minus 1.28, right. Now, first we will calculate the standard error of the mean. First calculate this. Now, how much it is coming? Sigma upon root over of n. Sigma was 2 root over of 50. Okay. Using the formula, standardize the sample mean now. So, z is equal to how much? X bar minus mu hypothesized divided by the standard error, which is giving us a result of minus 0.88. So, where is minus 0.88? What was your critical value? Now, minus 1.28. Where is your estimated value? Minus 0.88. So, if I see, if we all see it, that means it is coming within the range. Okay. So, on basis of this you can say that we cannot reject the null hypothesis. So, otherwise some people also say we accept the null hypothesis. This standardized value on the z scale falls well within the acceptance region, yes, correct. Therefore, the hospital should accept, or again I am repeating, we should never say accept, we should always say we should not reject actually. Anyway, so this is normally this is used, but you should write in your any paper or publication or any thesis, it is not rejected rather. The null hypothesis, because the observed mean is not significantly lower than our hypothesized mean of 100 cubic centimeter. On basis of this sample of 50 doses, the hospital should conclude that the doses in the shipment are sufficient, right. So, because it is not below the lower level, right, of the which is there in the alternate hypothesis, correct. So, this is the second case where we did. Now, let us go to the third, one more case. Just what you can do is you can think of real life situation where you can face such kind of situations where you are dealing with one tailed, you know, and let us for example, I have given you several examples. Maybe for example, manufacturers try to make products and then they are worried that the quality of the product should not be too less, or the cost of the product should not be too high, right. So, what is the objective of your research? Accordingly you decide the null and the alternate. Okay. Now, coming to the third case. The third case is a case of hypothesis testing of proportions. Now, what are proportions? We know that proportions are nothing but a part of the whole, right. So, it is a part of the whole, it is some significant, it is a portion of the whole, right. So, what we are doing is, in this case we are dealing with large samples in this case. So, large samples, what do you mean by large samples? So, we have said in statistical terms, anything that is beyond 30 or larger than 30, we say it goes into the category of large sample, right. So, below 30 we say small samples and we use a T distribution, large samples are greater than 30 and it follows a Z distribution, right. So, now the first case is of a two tailed test of proportion. Now, let us see this. A company is evaluating the promotability of its employees, right. It wants to promote its employees. It is trying to determine the proportion of people whose ability, training and supervisory experience qualify them for promotion to the next higher level of management. The HR director tells the president that roughly 80%, how much? 80% of the whole, that 80% of the whole total of the employees are promotable, correct. The president, see, this kind of decisions will have an impact on the company. Now, how will it have an impact? Because suppose it is not 80% and 70%, so the extra 10% people are unnecessarily given extra money, right. So, the president assembles a special committee to assess this promotability. This committee conducts an in-depth interview with 150 employees and finds that in its judgment only 70% are actually promotable. So, out of the sample that they collected, they found that only 70% are promotable and not 80%. But the president does not want to take a risk. He says he wants to test at a 5% significance level that the hypothesis that 80% of the employees are promotable, is it true or not true. So, in such a condition, how would you proceed? So, this is not a case of means, it is a case of clear case of proportions, right. So, first again I would suggest write the null and the alternate, right. So, I am giving you a pause, you may just write your null and the alternate by the time, right. So, in this case what is the data? Hypothesized proportion is equal to 0.8. So, this is the proportion of success, correct. The failure is automatically 1 minus p. So, that is equal to q, which is equal to 0.2 for this one, right. N is equal to 150. Now, in the case of sample, because this indicates the sample, right, this is 0.7. So, q is q is equal to 0.3. What is your null hypothesis? Now, 80% of the people are promotable, but is that what he is interested? If he would have been interested, he would not have asked for a checking, right. He would have directly given promotion, but he is not doing that because he knows that it adds to the cost of the company. So, that is why the manager has taken, the president has taken interest in checking this one. So, this is what is of interest to him, right. So, he says P is not equal to 0.8, but he is not telling at this moment that P is less than 80%, because if he tells that, maybe the staff in his company might start thinking that this president is a very negative man, right, negative person. He is forcefully thinking that we are not promotable, or we are not efficient people. So, he does not take a risk. He says, well, let us leave it to the study. We will say ki it can be more than 80 also. So, if there are more than 80% of people, then we will give to everybody. What is the problem, right? Or at least 80% out of this, suppose 90% people are promotable, but at least 80% we will give surely. But if it is 70%, but actually heart of heart, that is what his interest is, right. Alpha is equal to 5%, we have said. So, again the alpha, that means will be spread up, correct. The company wants to know whether the true proportion is larger or smaller than the hypothesized proportion. Thus, a two-tail test of proportion is appropriate. Here you note, please, this is important. When you deal with proportions, the correct distribution is always binomial in nature. The binomial distribution should be used, because it is a fraction, it is always a part of the portion, it is not an absolute number, you are taking it a fraction. So, that is why the binomial distribution is a more appropriate distribution, and as the sample size increases, the binomial distribution approaches the normal distribution in its characteristics, and thus we can use the normal, the later one, that is the normal, to approximate the sampling distribution, correct. This is very important, kindly note. If you have a small sample size, then it will not approach the normal, thus you will use the binomial distribution, and in case of binomial distribution, for example, the formula will slightly be different. For example, the mean in case of a binomial distribution is equal given as is equal to NP, right. The standard deviation is given as root over of NPQ, okay. So, it is changing, right, and similarly the variance obviously will become square of this one, right, just NPQ. So, this changes because NP and NQ, this is another important thing that you need to remember, are larger than 5, which is taken as the minimum number. We use the normal approximation of the binomial distribution. So, from table 1, the Z value for an area under the curve of 0.4 is 0.475, because 95%. So, 95% divided by 2, 0.475 is the Z value is 9.96. Now, let us calculate the standard error. First thing is you calculate the standard error of the proportion this time. So, this formula has changed now. Earlier when you were saying standard error in terms of means, you were saying standard deviation by root over of n, correct. But here the formula has slightly changed, it has become P into Q upon n, right. So, PQ by n. So, that means if I say P into 1 minus P by n, right, root over. So, this is equal to, in this case, in our case, P was 0.8, the hypothesized proportion, Q was 0.2 divided by n, which was 150. So, 0.0327. So, the standard error of proportion is 0.0327, right. Now, let us calculate the Z value from this. Now, to do that, what we will use is the sample proportion the sample proportion mean, which is sample proportion, sorry not mean, sample proportion which is 0.7 minus the population proportion, right, hypothesized proportion which is 0.8, right, divided by the standard error. So, this gives us a value of minus 3.06. What was our acceptable value? 1.96, right. So, 1.96 both sides, right, 1.96, but now we are getting a value which is 3.06, right, 3.06. So, automatically we were allowing acceptance was up to this level, right, this was acceptable, but this is falling besides the acceptable limit. So, since it falls, the proportion falls outside the region of acceptance. So, in this case the null hypothesis is rejected. So, if the null hypothesis is rejected, the alternate is accepted. So, what was the alternate? The president should reject the null hypothesis and conclude that there is a significant difference between the director of human resources hypothesized proportion of 0.8, that means 80%, and the observed proportion of promotable employees in the sample. So, observed was 70%. So, there is a difference, right. He should infer that the true proportion of promotable employees in the entire company is not 80%. It could be either way, but it is at least not 80%, right. So, I will stop this class here, lecture here, and I will try to although in the next session also we will continue with hypothesis testing, because you see it is very important that in real life you understand the how to calculate and how to interpret the values. They are very important. Nobody is going to tell us in real life ki what values to be taken and all. So, you need to be very clear these things, and then only you can reject or accept your alternative, or reject your null hypothesis, whatever it, or accept your null hypothesis, whatever. So, these decisions can only be taken by the researcher when he understands this. I hope this lecture was clear. If there is any doubt, you can always put in your questions later on also, but I am sure this must be quite clear to you. And in the last class also I had explained to you how do you calculate the probability, the p value also, right. That was also very simple and but very important for any researcher to understand, because many a times when you use software you will not be given some of the values. So, the at least the description how they have arrived. So, there you might face confusion, and that is the reason maybe I have seen many a times researchers use statistical tools through the help of softwares, but the clarity is not there. So, this clarity has to be there, and it is very important, otherwise your understanding of the study is questionable, right. So, I hope you have understood for today. All the best. Thank you so much.